this has a lot of disadvantages. And there are several types of disadvantages. One is that when you want to minimize the empirical error as measured by this indicator function of making mistakes, so you want to minimize the number of mistakes you make on the set of data, it's in general very hard to do it computationally. For example, if you take hyperplanes in RD and you try to find the hyperplane that minimizes the empirical error, in the sense of minimizing this quantity here, it's exponential, it requires exponential time in the number of examples. This is more or less impossible to achieve. So that's one disadvantage, and it comes from the fact that the problem is really of combinatorial nature. You have to find, try out all possible hyperplanes and see what happens. So the idea is that maybe, and that's something that is often the case in computer science or algorithmics. When you have a hard combinatorial algorithm, you replace it by something a bit smoother. You introduce real valued quantities, and usually it makes things a bit better. But of course you lose in accuracy because you no longer minimize the same thing, you approximately minimize something. But you gain a lot in terms of computation. And that's the idea. You smooth a bit this quantity here, you replace it by something which is real value. So what you do is, first you replace your classifier by something that returns a real value, and then you use a loss function that uses these real values. Okay, so in the case, for example, of hyperplanes in RT, instead of using just the sign of the hyperplane for T, you use the linear function corresponding to the hyperplane. And then you use this information in the loss. Okay, and apart from the computational advantage, you have seen in the SVM case that as soon as you replace, and as soon as you take into account this linear functional, then you obtain a problem which is nicely behaved, which is quadratic programming you can solve easily. Well, easily. At least not this polynomial time instead of exponential time. But there is another motivation, which is that once you do that, once you replace this set of classifier by something which is a bit smoother, and when you have a loss which is a bit smoother, you also gain in terms of capacity of the class. For example, if we have, or remember, hyperplanes in RT have VC dimension t plus 1. So if you have a very high dimensional space, then the VC dimension increases. And it can be infinite if you have infinite dimensional space, which is the case of for certain kernels in SVM. But on the other hand, as soon as you take into account this information about the real valued output of your classifier, you may find out that the actual capacity of your class is much less than what you thought, so much less than what is measured by the VC dimension. And for that, you need to introduce scale-sensitive versions of the VC dimension. And well, actually, I may not even go through the details of the scale-sensitive dimension, but I will just show you what happens for the Radmacher averages, because now you're experts in Radmacher averages. And one other remark is that the value that you obtain as an output of your classifier, basically if you have hyperplanes, the output is the distance of your points to the hyperplane. This can be used to give you some kind of confidence in your classification. So you no longer have just the sign information plus 1 or minus 1, but you also have the absolute value that tells you how confident you may be in the classification that you are. So let's see some examples of such loss functions. So this L is my loss, so it's a function that takes as an input the output of the classifier, so this is a real number, and this is plus or minus 1. And it's reasonable to assume that this is symmetric. So if I look at plus 1 here, and g of x is the same as putting minus 1 here and minus g of x. So I want to have symmetric costs in the mistake that I made. And this naturally leads to functions that have this form. So a general, I mean, this is a bit more restrictive than this, but in the symmetric case, it's not much more, it's not restrictive. So all functions that are symmetric in the sense that I described before can be written in this way. And this quantity here has a very important role in the theory. It's typically called the margin. So the value will be negative if you make a mistake and positive if you don't make a mistake. And the absolute value will somehow measure the confidence or the distance to the hyperplane of G as a hyperplane. Okay. And it's called the margin of the classifier G at the point x, y. So now, so this is somehow a measure of the error, but it's not exactly the count of the number of mistakes that I made. It's some different measure of error, and we have to relate it to the error we are really interested in, which is the misclassification error, the number of mistakes we actually make. So first we'll do the same thing as before. We consider the true average of this loss. So if we sample points from our distribution, and we compute this loss phi of y g of x, and take the average over the distribution, then we obtain the loss or expected loss of G. And we can have equivalently measure the loss on the data and have empirical loss of the LM. And it turns out the same techniques that we have developed to relate the risk to the empirical risk can be used to relate the loss to the empirical loss. And we can also play the game of introducing this extra class of function by just mapping one G to one F in this way. So for each G, we define this loss class. And once we have done this, then this is just PF and this is just PNF. So we can just go through the previous slides and we have the same bounds, essentially. Okay, I'll give you some examples of loss functions of this type. So here is the margin. So this quantity y times g of x. And this is 0. When we are below, we are making a mistake, and when we are above, we don't make a mistake. Now, what kind of function phi can we take? If we want to measure the number of error, we just have to take this indicator function, which is 1 when we are negative and 0 when we are positive. And that would count how many mistakes we make. And a reasonable thing to do is to replace this, which is a bit not well behaved, so it's not continuous, by something which is smooth enough and that is an upper bound on this. Because our goal in the end will be to minimize this error. So if we minimize an upper bound on this error, then it's likely that we also minimize the error itself. So we can consider various types of functions that are upper bound on this function. So one of them is the green one, which is called the hinge loss. That's actually the loss function that is used in SDN. And it's linear here. Its value is 1 at 0 and 0 at 1. Okay, and on the next slide you see the expression of it. It's this one. So phi of x is 1 minus x when this is positive or 0 when it's not. Then you can also use squared error, which is this light blue curve here. And it's just this one, 1 minus x squared. And why is this the same as the standard squared error? It's because, so phi of x is 1 minus x squared. And remember, x is actually, this guy here is y times g computed at a certain point x. So x is not the same here. So this is the correct expression. Phi of the margin y g of x is this. And since y is plus or minus 1, it doesn't matter. We're taking the square. We can multiply the whole thing by y inside the square. and y times y is 1. So this is equal to this. Okay, and somehow this is the standard squared error that we would use in regression, for example. So it's not different. And okay, there are some other possible choices. Okay, there is the red one which has disappeared. The red one, which is the squared hinge loss, is the square of the green curve, which means it goes like this. And then here it's 0. And the exponential loss, which is here, it never goes to 0. Okay, and well, basically you can pick any of those functions and try to minimize it, and that will give you a reasonable algorithm. But how reasonable? That's the question. It will basically depend on what you obtain when you minimize this loss. What will you obtain is the following. Okay. So, if we look at the specific position x, the label can be either +1 or -1, and the probability that it's +1 will be related to what I called, what did I call it? The regression function, eta of x, was it's just the expected label, eta of x, the expectation of y given x. Okay? So when there is a probability p of obtaining y and 1 minus p of obtaining p of obtaining 1 and 1 minus p of obtaining -1, then this is what is it? P minus 1 minus p, which is 2p minus 2. Okay, so there is a relationship between the probability of having positive label and the value of this regression function. And that's what I used here. So for each x, forget about the expectation right now, but for each example x, there is a probability 1 plus eta of x over 2 of having label +1. And if the label is +1, then the loss that I incur is phi of +1 times g of x. And there is a probability 1 minus eta of x over 2 of obtaining label -1, and in that case, I incur the loss phi of minus g of x. So this whole thing here is equal to the expected loss of g under the distribution. And okay, you can separate, well, this is not. There should not be an expectation here. Essentially, there is only expectation with respect to x, and this should not be expected. So the idea is now we want to find the best function as measured by this loss. So the best function as measured by the classification loss, we know what it is. It's the target, the base classifier. Question is whether when we minimize these fuzzy losses that I plotted here, do we also obtain the base classifier? Well, it depends. Depends on the loss. To check what you obtain, what you have to do is minimize this quantity for each fixed x. And that's what is written here. So for each value of the regression function, you have to find the alpha that minimizes this quantity, right? That's corresponding to this. And the best loss will be achieved when you take for alpha the value that achieves the infimum, and you take for each x you take alpha corresponding to eta of x, which is what is written here. So minimizing the expected loss can be achieved by minimizing it pointwise. So for each fixed x, you take the minimum of this, and you construct a classifier that more or less returns you this optimal value at each point. If we do that for the classification cost, the 0, 1 classification cost, we obtain the base classifier, and otherwise we obtain different classifiers. And I think I have written that here. No, it's not written here, but I can tell you the result. Maybe it's later. So there are actually two types of effects. A very interesting case is this inch loss. Remember phi of x for the inch, or let's write this yg of x. So plus means we take a value when it's positive and 0 when it's not positive. So when we minimize this, if we minimize the expected value of yg of x, of phi of yg of x, and we minimize, then the optimal classifier is the target function, the base classifier. And that's a very interesting property. Even though we minimize something which is not what we want to minimize, which is an upper bound on what we want to minimize, we still are in good shape because the optimum function is the base classifier. Well, actually, it's not exactly true. The base classifier is a minimizer of this, but there are other minimizers. So it's not unique, but it's still among the minimizers. So when you minimize this, the value of the minimum is actually twice the base error, which I don't remember. Yeah, r star. So the optimal value of the loss is twice r star. Why is that? It's because, remember, this loss is like this. That's the inch loss. The base classifier returns us either +1 or -1. When it's +1, it means we have not made a mistake and we pay a price 0. And when we make a mistake, we pay a price of 2. So that's why we have this factor of 2. It's just because the loss is rescaled compared to. So that's the loss that we should minimize. That's the loss we want that we minimize when we do this. And the difference is that instead of paying 1 for every mistake, we pay 2 for every mistake. But the optimum is the same. That's very interesting. Now, if we take instead the squared error, if we put squared here, then the minimum is the regression function. This star is eta. So that's really different. Of course, the sign is still the sign. So remember that the sign of eta is the target, the base classifier. But now our optimum function with respect to the squared error is this function that takes arbitrary value, not only +1 or -1. It has the correct sign, which means that the sign of this best function when we minimize the squared error will actually match the sign of the base classifier, but it's not the same value. And that's quite interesting, because it means that what you do when you minimize the squared error is different than what you do when you minimize the hint loss, especially when you have noise. Let's say this is x, and let's say this is your regression function eta. So it's the probability of having label 1 when you are at the given point x. If you minimize the squared error, trying to minimize the squared error is trying to find this d star, which is eta. Which means you try to find a function that is as close as possible to this. Right? So what is important with respect to your loss is to minimize this square distance between those two functions. That may be difficult, especially if you have lots of little bumps here. Whereas if you minimize the hinge loss, you are very happy as soon as you have a function that, say, does like this. Here you have optimal function with respect to the hinge loss and also with respect to the classification error. Because this doesn't make any mistake. If we take the sign of this yellow function, it does not make any mistake. So we really have two different behaviors. If we minimize the square error, we try to fit all these little bumps, and that may take forever, especially if the regression function is complicated. Whereas if you want to minimize something like the hinge loss, we don't care about these bumps. What matters is when does the regression function changes its sign, which is exactly the decision boundary when the decision switches from +1 to -1. So that's something that really tells you that it's not stupid to minimize the hinge loss. And when you say, well, okay, instead of minimizing the hinge loss, I can minimize the squared hinge loss, that's standard, what is it called, L2 SVM, or I can take the squared loss, it's not more or less the same, so it's the least square SVM. It's not the same. Okay, maybe in practice it will give you similar result because this kind of ugly cases is not very, does not happen very often. Maybe most of the time the regression function is smooth enough so that estimating this is not harder than estimating the whole regression function. But you have to think of what you're doing and what kind of assumption you need to make your algorithm work. So that's more or less the message of this lecture. Okay, so we can go next to the next lecture, I guess. Okay, so again I'll do some very vague explanation of all this. So regularization. I told you before what that is, quickly, but I will explain a bit more. So, and Vladimir also mentioned this regularization method for solving import problems. So in certain sense, you can always formulate, or most of the time, formulate your learning algorithm as something that plays a trade-off between a fit of the data and complexity of the functions. And you can, most of the time, even write this trade-off as a sum between two terms. So, for example, in the NTL case, you have some kind of, you code the errors that you make on the data, and this is kind of a fit term, and then you add to this the length of the code that you need to encode your hypothesis. That gives you another term, and you try to find the best compromise between those two terms. Support vector machines, it can be written exactly like this. I don't know if Bernard showed it. I will come back to this in the next slides. Not many algorithms can be written in this way. Bayesian algorithms, not really, because they don't just take one function in the class, but they take the whole distribution of posterior distribution of the class. But the mode of the posterior is the one that minimizes some kind of quantity like this, where here is the likelihood, and here is the log prior, minus log prior. Basically, most algorithms have this flavor. Maybe not exactly this form, but this flavor. And it turns out you can rewrite this in other ways. Actually, I think historically, this was not the first form that was proposed. I don't know, let me let you know. version was the first to be proposed? This one? Ivanov. This is Ivanov, this is Tikhonov?
Yeah.
Yes? Okay. So, different people propose different version of this, and I think Basim showed that they are right for them.
But it's happened very short time.
Okay, so, I mean, yeah, around the same time, all people realize that these things are more or less the same. And why are they the same? This is the explanation. If you look at the set of solutions that you obtain for this minimization problem when you vary lambda, so you take all possible non-negative values for lambda, and for each value of lambda, you take the best function f lambda. And you create a big set with all these functions. Okay, that's one thing. Then you do the same here. For each value of e, you create a set of solutions. Solutions corresponding to minimizing this term with the constraint on the error. And the same here. You take all possible values of r and you minimize it for it. Then the sets of solutions that you obtain are all the same. So what does it mean?
The way you present it, it looks like it's obviously the same. Like right on the first one. Or
yes.
So it's not the case that it's obviously the same. There is some.
There are some conditions. You cannot take just anything. It has to be, well, there are some. For this has to be increasing, for example. I can't remember. There are some implications that are obvious. The Lagrangian, of course, requires some convexity, for example, or something like this, of the functional. So it's not like you cannot just plug anything here and obtain the same thing. So, but under suitable conditions, let's say, these sets of functions are the same. But the trick is that if you minimize this for specific lambda, and you say, well, now let's try to do it in this way, so let's try to find the R for which the solution of this problem is the same as this, then it's not straightforward. And it's even worse than that, it depends on the data. So the relationship between one lambda and the corresponding R, so the R that gives the same solution, is data dependent. So you cannot say, well, okay, let's, in general, R is square root of lambda, for example, and then we have the same solution. That's not the case. So that's why these problems are a bit different when you want to implement them. You get into, I mean, you really have to make a choice, and depending on this choice, you have a different algorithm. And actually, the new SVM is another flavor of this, where you have another parameter which is new. And right? If we want to compare it with these formulations, the new SVM problem would be maximizing over f mu minus empirical error of f divided by, so the norm of f, so it's like omega of f. This one, the new SVM is also a regularization problem equivalent to those ones. So for the choice of mu, there is a suitable choice of lambda that gives the same solution, but which has this form here where we have a ratio between this and this. And maximizing this means we want to find small error and small norm at the same time. Okay, so some remarks. So, in some sense, they are all variants of this SRM principle that we presented. Because what we do is nothing but trying to trade off complexity and error. And okay, it's also a variant of what is called model selection by penalization, where we have a set of models and we try to find the best one, adding a penalty to the error. So they all boils down to this problem somehow. The key thing is to choose this function here. So we have seen how to choose this loss function. Well, not in detail, but we have seen some guidelines to choose the loss function. You have to find the loss function that is an upper bound on the misclassification error, and that makes sense in the sense that it's when you minimize it, you recover something which is related to the basic classifier. So this is okay. We know how to do it. Now the question is how to choose this regularizer. So one possible way is to start with a set of functions. That's the SRM approach. You have a series of nested classes of functions with increasing VC dimension, and here you just put the VC dimension of the class in which it lies. But there are other ways of doing it, and in particular, the VC dimension thing may not be easy to handle because you have to minimize the empirical group error or some error, some loss in classes of VC dimensions, of integer VC dimension. So it's again some kind of combinatorial problem in some sense. Whereas as soon as you use this kind of formulation here and you allow real values for this functional omega, then you may have some nice smoothness properties or convexity properties of this functional that allows to solve this problem directly, and then you just have to play with this parameter lambda instead of playing with the parameter of the VC dimension, which is a bit less easy to play with. I just give you some idea of what is the influence of this function of omega on the capacity of the functions, of the class of functions that you obtain. What is the class of functions you obtain? Or the class of functions you should look at, given this equivalence of all these problems. In some sense, you can say that when you minimize this, effectively you are working in classes that have this form. Omega of f is less than a certain constant. So, if you want to say something about the capacity of your class of function f, you should not look at the whole class f, but rather look first at bolts like this, omega of f less than r. And in general, these bolts, this omega can be a norm. So in the SVM case, omega of f is just the norm of f in a certain space. Square norm. So this means the relevant classes of function are, let's say, f indexed by r, is the set of functions that have norm less than r. What is this? This is a ball. Okay? This has a very specific, nice convex shape. And not only does it have this shape, but also there is nice relationship with Radmacher algorithm. Remember, Radmacher algorithm involve this Rn, which I told you was linear functional on the function g. So now if we want to compute the Radmacher algorithm of such balls, we have to compute this quantity. So expectation with respect to the sigmas. Remember, inside here I have 1 over n sum of sigma I g of xi. And I want to do it on a ball. So I have a constraint on the norm of g, like this. And there is a very nice property which is summarized here, which is that when you look at the supremum in a ball of a linear functional, then what you obtain is the norm of this linear function in the dual space. Okay. So let's write it in a simple way. So assume we are looking at linear functions only. We we're looking at the set of W's that are less than R in norm. And our classifier somehow G of X is W inner product with X. Okay, so just a linear classifier with weight W. And let's say we want to compute this run marker of this ball, so W less than R. And this is the expectation with respect to sigma of the supremum in my ball of 1 over n, okay, sum of sigma I size times the function evaluated at the x size. So W xi. And I write it in lowercase because they are fixed. I'm looking just at the conditional run marker operators computed on the data. Okay, so one way to rewrite this, so that's the linearity somehow of the functional, which here is obvious from the choice that I've made, but in general, you also have linearity in a slightly different way, but it does not really matter. So I maximize this. So let's take even the 1 over n outside. And here I have what? I have W inner product with sum of sigma I xi. And it's an easy exercise to show that this is actually equal to, so you have this 1 over n here, times R, times the norm of what is here. Actually, Cauchy-Schwarz will tell you that this is less than the norm of this plus times the norm of this, so R times the norm of this. But when you take the supremum, it's actually Cauchy-Schwarz becomes an inequality. So in the end, what you're saying is R over n times the expectation over sigma of the norm of sum sigma I xi. Okay? And I have some so let's conclude this. See what it gives us. So we want to compute this expectation here. So what is the norm? The norm is the square root of the inner product of the vector by itself. So we have to compute this. Okay. Now, square root is a concave function, so we can use Jensen's inequality. And this is, so expectation of the concave function is less than the concave function of the expectation, so that's the opposite of Jensen, which is for a convex function. This is less than the square root of expectation of this whole thing. And by linearity of the inner product, I can also rewrite this as a double sum over I and j of sigma I, sigma j, xi, and j. Okay. Now, expectation is linear, so I can take it inside sum. Whenever I have two indices that are different, because these signs are independent, the expectation of this product is the product of the expectations by independence. And you know that, you remember that we had the probability 1/2 of being 1 or -1, so the expectation is 0. So all terms that are I different from j cancel from this sum. And we are left with the terms where I equals j. And for these, the sigma does not play any role, it's always 1. Right? It's plus 1 times plus 1 or minus 1 times minus 1, so it's always 1. So what we are left with is no expectation and just sum over I of xi. Okay, so if I rewrite the whole thing, I have that the rad factor average of it's not a good case to write this R, but okay, let's stick to R. Is upper bounded by 1 over n, R over n, sorry, square root of the sum of the norm of the xi's. So that's the result I obtained. If we want to relate it to the bound of the BC dimension of hyperplanes with margin at least gamma, so that's what Vladimir showed yesterday. So let's say remember the BC dimension of hyperplane with margin. I don't remember the notation. I think it was delta. This is roughly delta squared, and here delta. And here the radius of the wall, so it was denoted by r. Here r is a different quantity, so I will point p. So that's the radius of the ball that contains the data. That's the margin of our hyperplanes. And the margin, I think we saw that in Bernard's talk, is related to, is actually the inverse of the norm of W, the weight vector of the hyperplane. And so this, when x is in the ball of radius b, this is less than n times b. So we have r over square root of n r square root of b or n. And I think I forgot the square here. And now how to relate it, we know that r is 1 over the margin. There may be also a square missing somewhere. Yeah. So essentially here we have square root of b squared over n gamma, which is BC dimension over n, square root of BC dimension over n. So we recover the same results, but using this nice properties of the relevant boundary. Nice. So I see you this afternoon for the survival.